So let's go with the second lecture on tomographic reconstruction. Again, some of the slides have been taken here and there from François and Brian Geiser as well, but most of them are still from me. All right, so I mentioned in the previous lecture on reconstruction that we end up with a number of parameters for the reconstruction, and some of those might need to be calibrated. So the main parameters are here: the detection efficiency, for example, the atomic volumes, the image compression factor, and this product of the field factor and the field, or the SHANK angle and initial radius, or the initial and final radii. All of these are parameters that will fit into the model. So why do we need to calibrate the reconstruction? Because if I look at this old data from Lee's PhD back in the day, so that's a small volume of an aluminium silver alloy. And if you start playing around with the parameters, you see that you can basically get whatever you want, from small platelets to sphere. So these are supposedly spherical Guinea-Preston zones in aluminium silver, and but you can also get needles just based on changing the K factor, the field factor, the efficiency, or the image compression factor. You can distort the volume in whichever way you want. So how can we actually do the calibration of the reconstruction? Let's get back a little bit to what the specimen shape is like. So typically for crystalline material, we end up with a series of terraces at the specimen apex, or the end of the needle, corresponding to the set of crystallographic planes. Once again, we've seen this in the previous lectures. It is well reflected when we do field ion microscopy. But when we do atom probe, very often we end up with a figure of poles, and if we can identify these sets of poles corresponding to this set of planes, we can actually make use of this, because the distance between the poles is a reflection of how much compression there is. And so, for example, if we go back to what I explained in the previous lecture, we can look at the distance between the poles, retrieve what is the observed angle between sets of atomic planes, and simply then compare this angle to the crystallographic angle between two sets of atomic planes, which are fixed by the crystallography. So in that case, this is for pure aluminium. We can identify all of these poles based on the local symmetries, and maybe a bit of experience, I would say. And then make use of this indexing to calibrate the reconstruction. This can be done quite often, actually. The pole figure will depend on the orientation of the specimen and the crystallographic structure of the material, and it might also depend quite a lot on the analysis conditions, as we've discussed also in previous lectures. But ultimately, if I look at the angle between these two sets of planes, for example, or these ones, I end up with an image compression factor in the range of 1.55 in that case. But it will depend on the specimen and the analysis conditions. So don't take this value for granted. It's much better to measure it. It doesn't take that long. To determine the SHANK angle, this is a TM image of the pure aluminium needle, and it's not that straightforward, actually, because if you look far away from the apex, the SHANK angle might only be a few degrees, and as you get closer to the end, we see that it's going to start increasing to maybe 5, 7, 8, 10 degrees. And I mentioned this in the previous lecture. It's not necessarily very straightforward, actually, to decide which is the SHANK angle that we should use. And we are going to analyze a few hundreds of nanometers typically in a specimen. And you can see that even there's like a continuous range of SHANK angles that might actually fit the specimen, the outer shape of the specimen. So which one is the right one is difficult to say. And for the radius of curvature, it's kind of the same, right? Because if we start just looking at the apex itself, it might be a bit smaller than if I take the outer edge of the needle. And that's not an insignificant difference. There's 20 nanometers out of 60, so it's a 30% difference between one and the other. So there will always be some inconsistencies and potentially some difficulties to get a unique value. But if I take this specimen that I analyzed afterwards, using a 3.5 degree for the shank angle and about 80 nanometers, I still get interspacings that are between the O2 planes, that was quite off. So it's still not that straightforward, even using a TM image of your needle to get the right parameters. And using the SEM, it can be even harder because there can be projection effects, and it's really not that simple. And there's also calibration issues with the SEM that might be a bit worse than on a TM typically. So you have to be very careful to not take for granted everything that you think you're getting out of these measurements. For the image compression, we can, for example, use the field and microscope, which can be done typically in the LEAP 5000 XS. So in that case, we sometimes see poles a bit more clearly, and then we can use whatever is in the literature or knowledge to determine these sets of planes and use the same protocol as I've discussed before with the ratio of the crystallographic angle to the observed angle. In FIM, back from the 50s, people actually started discussing how this series of rings that we see can be related directly to the radius, because effectively every time you go from one terrace to the other terrace to the other terrace, you're going to go down by just one interspacing, which means that the size of the terraces will be directly dependent on the radius, and the number of terraces between two sets of atomic planes can inform us on the local radius. So this is a well-known formula that was first used in the 1950s by Drexler and Wolf, and can be used fairly easily when you start dealing with field and microscopy images. The shank angle can also be determined if we start field evaporating in field and microscopy, because we know how many layers we've gone down in depth. So we know the depth, we know the increase in radius, so in principle we know the shank angle can be determined fairly accurately. This is the formula that you can use based on the number of planes that you've field evaporated, final radius, initial radius. Again, this is all fairly straightforward. For those of you who think, oh yeah, it's field and microscopy, I can't actually use it, the pattern that we see in the field desorption image or on the detector map, sometimes we can actually retrieve this ring pattern also from the detector impact positions. And so we can actually see the rings and measure the ring radius directly from the detector coordinates, do the same types of fit, and get an idea of the radius of curvature. And in that case, we can actually know almost everything about the specimen, the radius, the K, the image compression, all just by looking at the detector coordinates. There have been a few attempts to make this more straightforward, but I think this is lost in the noise of what gets published. But in principle, we could analyze directly these types of patterns automatically to find where the poles are and find what is the distance between the center of the pole and the successive rings corresponding to the local radii. To make sure that we are doing the reconstruction right, we need some criterion, and typically this is why we use some structural information from the specimen. So if I look back at this pure aluminum dataset and look at slices through this dataset along two different zone axes, we can see a series of planes corresponding to the 002, the 113, the 115, the 111 planes. In that case, the 002, 206, 204, 202 planes, with spacings that are approximately okay. But we need to be able to statistically measure this spacing. So there are a few approaches. One that's quite famous is the Fourier transform. It's typically what is happening when you do diffraction. Either with X-rays or electrons, same idea. So we can do the same thing and calculate this Fourier transform directly by summing all of these functions based on the position. So you have to grade the reciprocal space, and then you take all of the atomic positions in the real space and then calculate the Fourier transform and see where you start adding up some of these higher intensities in the reciprocal space. And this was done back in the mid-90s in Oxford, and then really formalized properly by François Vurpillot in the late 1990s, early 2000s. And so I invite you to read that paper in Journal of Microscopy where they describe the protocol. We can't really do this in IVAS, but there are ways to access code that can do this. And then ultimately what we get is really similar to a diffraction pattern. It's just limited angularly because we only see a small angular field of view in the atom probe. Another way to look at the structure within atom probe data is this so-called spatial distribution maps. So it was inspired by the work by Torben Ball, and then built upon by Brian Geiser and Michael Moody. And the idea is quite simple. You take a small box, you take an atom that is at the center of that box, and then you build progressively, you put in this box all of the atoms that are surrounding this central atom. And then you move the box to the next atom, to the next atom, to the next atom, and so on and so forth. So what you're building is in 3 dimensions, the average neighborhood of every atom in the data set. And then you look where you actually have high densities of points. And if you have a crystalline structure, you might actually find that there are, on average, above one atom at a certain distance above it and under it, there is a high probability to find another atom. So you can do this. You don't have to do it in this way. You can do it in many other ways. This is a 3-dimensional radial distribution function from Dan Haley, for example. But that's basically the idea. And then what the SDM does is basically look at this distribution by histogramming either in Z or just in one slice in 2 dimensions. So if I get back to this pure aluminum data set and do an SDM or a spatial distribution map on these different poles, I can see these different sets of planes. And then looking at the distance between 2 peaks gives me the interspacing, so the spacing between the planes, the distance between the planes on average. How can we make use of this information to calibrate our reconstructions? Typically, once we have looked at the detector map, and if we see poles, we can calculate the image compression factor just based on the distance between poles. And then the only parameter then that remains to be fixed is this product of Kf times F, assuming that we know what is the efficiency and the atomic volume. So what we can do fairly easily is build a first reconstruction. And you can see here, you can see the planes. They are just curved because the parameters are wrong. And then I'm going to calculate the interspacing either using a Fourier transform or a spatial distribution map, get a value, and this value, assuming that it's off, I can recalculate a new field factor, which is basically the one that I had used for building this dummy reconstruction, times the square root of the distance, the theoretical distance to the one that I've measured. And this works every time, more or less. Sometimes it takes a couple of iterations, but it always works because it's quite deterministic. The total Z is proportional to kf squared. So if your total Z is wrong, you just have to adjust kf to get the Z right. So this works really quite well, and then you do this typically once you're happy with the interspacing. But normally within 1 or 2 iterations you should be fine. And you can do this directly in IVAS using the Reconstruction Explorer. You can't change kf directly, but you can change the initial radius, which is basically the initial voltage that you had divided by kf and the value of the field that you've selected. So all of this can be done very routinely, very easily. And then once you're, again, happy, you can just look at plenty of atomic planes and diffraction patterns that sort of make sense. So with this, in principle, you can actually get fairly accurate values of the field, the image compression factor, the field times the field factor quite accurately. It's not the end. There are many aspects of this that we need to always keep in mind. So it's not because you've measured ICF and KF once on one instrument that you're all done. The parameters change from one specimen to another. As you can see here, there's just like maybe 24 points, or maybe 1.5 dozen points from different samples. There's no real trend. You can see here 3 different pure nickel specimens, and the values are a bit all over the place. And that's just because it's really highly dependent on the geometry of the specimen. So if you have a higher shank angle or a higher radius, you're basically going to have to adjust your KF and ICF values. It's not that straightforward to predict. That's just a single specimen that we analyzed at increasing laser power, so increasing temperature at which the field evaporation takes place. And so what happens here, and I invite you to listen to the previous lectures on the laser pulsing especially, we can see that the radius of the specimen, as the temperature gets hotter and hotter, the radius of the specimen starts to change, and it starts to increase quite significantly. And in that case, the value of KF that we need to use to get an accurate spacing of the O2 planes keeps decreasing, and so does the ICF. So we can actually get an idea that there is a relationship between the radius and also the geometry of the specimen and the KF and the ICF. And these relationships are not necessarily super straightforward, but they're there. So be quite careful when you think you've got the best reconstruction in the universe. It probably is not exactly the case. And it will depend from one specimen to another specimen. You can't really reuse the same parameters. Going back to what we're discussing in the previous set of slides, as we field evaporate the specimen, we are basically going from a smaller, sharper specimen to a blunter specimen. We are peeling off the atoms progressively, so the specimen becomes bigger and bigger and bigger. So the radius increases, and I've just told you that for a larger radius, the value of KF and ICF also change. So if I take one single data set and look over the course of the analysis, can I see a change in the distance between poles, for example, that would be indicative of a change in the ICF? Can I see if I measure the change in ICF, can I build a reconstruction every time to get the right KF? And yes, you can. There's nothing preventing you from doing so. And we did this for a dozen specimens or analysis for different materials, so for some aluminum tips and some cast strip steel, so low alloyed high strength steels. And you can see that effectively as the radius keeps increasing, we get a drop in the ICF values and of the KF values, basically, because we fix Fe for iron here and for aluminium. So, and on average, it seems that the specimens from aluminium are always a bit bigger, a bit fatter than for the iron. So the values of the ICF and KF seems to be, or at least of the ICF is higher, and because here it's multiplied by the evaporation fields, the relationship is not straightforward, but KF also tends to be higher. So there is a relationship. We keep the ratio between these things, for example, and it does fluctuate quite a little bit. And there's some trends, but they're not always super straightforward. So if we look first just at the aluminium, we looked for the shank angle that we could measure from these specimens by looking at them in the looking at the way the radius evolved over the course of the analysis, and there's no real easy trend to be found there. You see here it's about 10 to 15, but here you only have a few degrees difference between the analysis conditions. But the orientation of the specimens is quite different. So here we have all one sample, here it's all one samples. So there's probably a role played by the overall geometry of the needle on the value of the KF and the ICF, and the ratio of these values. And this is for different specimens from the high strength low alloyed steel, and again the shank angle doesn't change that much, but the orientation of the specimen plays a bit of a role. But it's really quite hard to find really specific trends. If we look in the literature, there's some work that's been done to try and use exactly this parameter of the field factor divided by the ICF. And by looking at some modeling work, they predicted that it might be a constant, and they did this for a single shank angle or for multiple shank angles for the specimen. You can see slight differences. They predict that the ICF and the KF are linked by a cubic root relationship, and we don't really see this experimentally, although it's not completely off. But all of these parameters are interlinked because they are related to the geometry of the needle. But yet, at the end of the day, for now, it's not really straightforward to predict what the real and actual values should be. Right, so for now, we've looked at like mesoscopic issues associated to the reconstruction. And there are many other challenges, which I'm going to discuss right after. Challenges would be, for example, the difference in the field strength between the center of the terrace and the edge of the terrace itself, and this is what leads to these typical patterns. Because indeed, if we consider these atoms right at the edge of the terrace, and the expected trajectory should be a straight line, but basically there's always some subtleties in the early stages of the flight that will deflect the atom from where they're supposed to go. And these either it's due to the field itself that pushes the atoms away, or it can be the atoms that are actually rolling onto one another. And on this, I can only encourage you to read the recent work from Christoph Heisel's group from the Institute. There's quite a lot happening in this area that is really quite exciting. And beyond these effects of terracing and the field distribution, if we were to consider just one solid atom, for example, that requires a slightly higher field compared to the surrounding matrix, then have a case where all of the atoms surrounding this one high field solute would start to field evaporate, and then more and more will go up until the point where very locally here the field is high enough for this one atom to go. Thing is, the right atom should have been field evaporated amongst the first 12 atoms, and now it's field evaporated like 50th or 100th atom. But we use that sequence to build the Z, so how is this going to be affecting our performance? So I played a bit with this a while back. I just took the sequence in which I was detecting ions from within a pure aluminium data set, and I started randomizing the order in which I was reconstructing the ions. Initially in a small window of maybe 10 ions. So you can see I swapped just the positions, and then I go to the next 10 and I swap their positions, and then go to the next 10 and I swap their positions. And then I do this not only for 10 atoms, but maybe for 50 atoms or 100 or 1,000 atoms. And I build the reconstruction, and then I look at what the data looks like. And you can see that if I randomize over maybe 1,000 atoms, the difference is not very big. 10,000 starts to be a bit visible, but 25,000 atoms is very clearly degraded. And for 50,000 or 100,000, atoms just appear to be completely random in the data set. These are the exact same ions that I've detected. I'm just reconstructing them in a slightly different order. And you can see there that basically this ruins everything with respect to the depth resolution. So we need to somehow find the best possible ways to control the order in which the atoms are being field evaporated and hence reconstructed. And this is why we need to control the field when we do the analysis. And this goes back to one of the previous lectures. It's all interrelated, you see. Also, when we start looking at these types of very local curvature, because the trajectories of the ions are related to the field, if you have a local high curvature, there's a local high field, which is going to push the ions away. So we will actually have trajectory aberrations related to this. And again, if I start looking at not just one atom, but multiple atoms, you can actually have atoms from this particle here that requires a high field, that instead of being field evaporated and fly straight, are going to be deflected to the side and end up being imaged alongside atoms from the matrix. And these are these so-called local magnification effects and trajectory aberrations. These have been well reproduced by finite element method simulations, and we can typically trace them back based on the point density on the detector. So precipitates with a low field typically appear very dense on the detector and hence inside of the reconstruction. And you can see an example here, for example, from the simulations. Precipitates with a high field appear less dense, and they would look more like that. So here are two examples. The magnesium zinc rich precipitates in a 7000 series aluminium alloy, typically what Huan Zhao has been working on here for the past few years. And you can see that if I look at regions that are very dense in the data, I end up with imaging the precipitates themselves. And I can look at the opposite, which is the beta prime or beta double prime precipitates in a 6000 aluminium alloy series, where here I can see that I'm just imaging where the low density regions are, and I end up with imaging the precipitates. So these are very well-known cases. And then you can end up with both combined, where you have, for example, here a scandium rich core and a lithium rich shell, and an aluminium lithium scandium alloy. And you can see that the particles are stretched in one direction. The shell is stretched along the z-axis because the lithium has a low evaporation field, so will come too early during the field evaporation. Whereas the scandium actually requires a higher field than the surrounding aluminium matrix. And so it's going to be distorted in the XY direction mostly. This is not pretty, but that's just the best we can do with the current reconstruction paradigm. And when you start looking at multi-layers, things can go really bad because the different layers will start to field evaporate at different times, And you can see here, for example, the iron cobalt layer will come much earlier than the MgO layer, so you'll have changes in the specimen shape, and they are going to result in fairly complex patterns in the sequence in which ions are detected. There are many efforts happening at the moment to try and make this a bit better, and we can discuss this in a separate presentation later on. This will conclude our 2 lectures on reconstruction. So some things to bear in mind. The reconstruction protocol processes ions sequentially. So first we reverse project the detector impact position onto a virtual emitting surface. Historically this was flat, now it's curved, so we actually reposition this onto a curved surface, and then we move this surface down just by a small increment that is proportional to the expected volume of an atom inside the material, and inversely proportional to the efficiency and the analyzed area. This protocol, which was proposed by Ba et al., builds on the works from Blavet in the early 1980s. It was improved slightly by Geiser, especially for the SHANK angle reconstruction, but it still doesn't really allow us to account for the very complex shapes that the field evaporation provides to the tips, and the field emitting surface that is really not a spherical cap. And this becomes really particularly problematic for materials that are compositionally complex, with multiple phases, interfaces, and so on and so forth, which are basically our bread and butter. So we just need to be a bit careful. Typically, when calibrated properly, this protocol still yields highly precise reconstructions and results that are, the best we can do for now. But often I get asked, what is the resolution? And it's really difficult to pinpoint this, and I'll prepare a separate lecture on these aspects. So don't fall into the trap of saying that atom probe has atomic resolution. It's really not very true. And we need to always be a bit wary of the fact that there are trajectory aberrations taking place no matter what. So there's always a bit of error that we need to take into account in the discussion of the results. On this, thanks for your attention, and I look forward to the next set of slides that you will be able to listen to.